So far, we've talked about descriptive statistics in terms of presenting and visualizing numerical data and categorical data. We now also want to consider more generally, right, what statistics is about and also how we can think about the world around us. Statistics often entails studying what we call random phenomenon. Right? This is where probability comes into play. Probability deals with random phenomenon. Now the thing about random phenomenon, right? Life is filled with random phenomenon, but it doesn't mean that it doesn't mean that it's entirely chaos. All it means is that there's some degree of uncertainty. The world is pretty structured. You might go to work. You might drive in a certain way on a car, and you expect to get. If you're commuting to a certain workplace, you might expect to get to your workplace in 30 minutes if you're driving, let's say. But there's still some uncertainty. Right? Maybe it's 35 minutes. Maybe it's 25 minutes in terms of your commute time. That's the idea behind random phenomenon. We're not saying it's complete chaos. We're just saying that there's some uncertainty in life. And the way we can quantify and understand this uncertainty is through probability. This is the basic idea. When we analyze the social world, there are random phenomena, but we can impose some kind of structure to help us understand the world by specifying possible outcomes for each repetition or trial of the random phenomenon. These outcomes, they must be exhaustive and mutually exclusive to accord with the rules of probability. So let's think about this, right? When we talk about properties of outcomes. Collectively exhaustive just means that all possible results of the random phenomenon must be listed. Mutually exclusive means that the outcome of the random phenomenon cannot fall into two outcome categories simultaneously. And then the sample space is a list of all possible outcomes from some random phenomenon. So let's think about imposing this structure, okay? The next task is to assign probability values to each event or each particular possible outcome. We denote the probability of the event or outcome A as the probability of A, which we can shorten as PRA or PA. The probability of some event or possible outcome A is the chance that A will occur, ranging from 0 to 1 inclusive. Right? A probability of 0 says it's unlikely to occur. A probability of 1 says it's an absolute chance of occurrence. Most events or possible outcomes in life are not 0, they're not 1. Right? Most events are somewhere in between. So when we talk about the probability of an event, right, when it comes to categorical data analysis, right, we can think about probabilities in terms of contingency tables. To put another way, one can understand probability as the observed frequency of an event in a set of data. We can view each case or observational unit of interest as a trial. Right? So this is the idea behind the probability of an event. It's the number of trials in which the event did occur divided by the total number of trials. In a data set, suppose you have a random sample of 100 people, right, and 50 of those people are men. So you might say the probability of being a man is 50 divided by 100. Probability of being a man is 1 out of 2, or 0.5. That's all probability means. When we work with probabilities, we have several rules that are really useful. And you'll see this when we work with contingency tables converted to probabilities. The addition rule is a very useful one. We can talk about joint and disjoint probabilities. Joint probabilities simply means that they can occur at the same time. Disjoint probabilities cannot occur at the same time. So here's an example. You might say a disjoint probability is being in London and Rio de Janeiro at the same time, in the same moment of history. Those are disjoint. Right? The probability of being in those both places at the same time is 0. But what's the probability of being in London and having a pint of Guinness at a pub? Well, that's probably a joint probability. Okay? Those can occur at the same time. We can visualize this in terms of two overlapping circles on a Venn diagram for a joint probability and two non-overlapping circles for disjoint probabilities. One point to keep in mind is that when we talk about the addition rule, we are trying to find the probability of A or B, where OR comes from set theory and logic, and so it has a different meaning than what you might expect. The probability of A or B means the probability of A occurring, the probability of B occurring, or the probability of A and B occurring at the same time. At least in the English language, a lot of people will say, they'll use OR in a way that means one outcome or the other outcome without considering that they might occur at the same time. So somebody might say, are you going to the grocery store or are you going to the gym? Well, without considering the fact that you might do both at the same time, that's what we really mean by or. Okay? The probability of A or B takes into account the fact that A and B might occur at the same time. And the addition rule says that the probability of A or B equals a probability of event A plus a probability of event B minus a probability of A and B. We subtract the probability of A and B so we don't double count that intersection. That can be seen here. Okay? So if we don't subtract the probability of A and B, then we're going to double count that middle part, that overlapping part, if the two events can occur at the same time. Right? And we give an example here. That's the basic idea of the addition rule. You can also re-express the addition rule in this way. You can say that the probability of A and B occurring plus the probability of A and not B occurring plus the probability of B and not A occurring equals the probability of A or B. It's just a different way of expressing the addition rule. Besides the addition rule, which allows us to find combinations of probabilities and work with probabilities, we also have this idea of conditional probability. We express it this way. That vertical line, right, that tells us given. Right? So the probability of A given B, that's a conditional probability. It tells us the probability that A occurs given that B occurs. One way to think about a conditional probability is just you're subsetting what you look at. Rather than looking at everybody, you might say, now what's the probability of working for an investment bank given that you graduated from Harvard? Looking at those people who graduated from Harvard, just those people, what's the probability of working at an investment bank versus what's the probability of working at an investment bank? Not conditional, not subsetting to people who graduated from Harvard. That's all conditional probability is really telling us. To work with conditional probabilities, it's useful to think about the multiplication rule. Okay? The joint probability of events, the probability of two events occurring at the same time, we can write as the probability of A given B times the probability of B. In a similar way, we can say that the probability of A and B equals the probability of B given A times the probability of A. The multiplication rule is useful because it can help us find joint probabilities, the probability of A and B, when we have conditional and unconditional probabilities. You might ask, what if A and B are independent? Right? If A and B are independent, then the probability of A given B equals the probability of A. Right? The idea behind an independent event is that knowing something about B occurring won't tell you about whether A will occur. That's the idea of an independent event. The multiplication rule simplifies when events are independent. The probability of A and B is simply the probability of A times the probability of B. This is why independent events multiply together. Right? They're easier to work with when we have independent events. Well, one thing to keep in mind, though, is that in the social sciences and humanities, when we work with real data, with real people, probabilities really usually aren't independent. Right? So there's usually some degree of dependency between two or more events. One way to write the multiplication rule, right, just a different way of re-expressing it, is in this format. You can use a joint probability and an unconditional probability to find a conditional probability. So we might say the probability of A given B equals the joint probability, the probability of A and B occurring at the same time, divided by the probability of B. Or you can rewrite it so that the probability of A is in the denominator and you're finding the probability of B given A. These are just different ways of re-expressing the multiplication rule that we have just discussed. Some people also find it useful to write out and visualize the multiplication rule in terms of probability trees. The idea behind a probability tree is that you can find different probabilities conditional on other probabilities. So we can say, what's the probability of A given B? Well, right? You can find it with this kind of graph. Okay, you multiply across and you add as you go down. Now, the reason we talk about conditional probabilities is that it's very useful for calculating a commonly used measure in a 2x2 contingency table, a table where you have two binary categorical variables. So you have one variable with two levels and another variable with two levels. You can calculate something called a relative risk or a risk ratio. It's often used in public health, in epidemiology, and many of the social science fields. The relative risk is simply a ratio of two conditional probabilities. It's a probability of some event occurring given you've been exposed to something, divided by the probability of that same event occurring given you're not exposed to some some sort of risk factor, you might say. Exposure could be cigarette smoke. Did you grow up exposed to cigarette smoke? Did you grow up in poverty? And the event might be some outcome of interest. Did you graduate from college? Do you have a disease? The idea behind relative risk, it gives the direction magnitude of association for two binary categorical variables. So it's used when you have a contingency table of two categorical binary variables, and in particular, you're interested in some event given some exposure. Right? Typically, the adverse event is considered the event. So typically, we're interested in no health insurance, or that's why we call it a risk ratio, because we want to find what's the risk of getting the disease, what's the risk of not graduating from college. It doesn't have to be that way. It doesn't have to be set up that way, but that's typically how people use the relative risk or risk ratio. That's because it comes out of medicine, where people are interested in what's the relative risk of having a disease given some exposure. How do we interpret relative risk? Well, relative risk of 1, it means that there's no difference in risk between the two groups. There's no association. Relative risk of less than 0 tells us that the event is less likely to occur in the exposed group than the unexposed group. Right? So for example, if you're interested in not graduating from college, given poverty, okay, if you have a relative risk of less than 1, right, means that not graduating from college is less likely to occur in the exposed group. Relative risk of greater than 1 means the event is more likely to occur in the exposed group than in the unexposed group. So when you have a relative risk of less than 1, it implies that this exposure has some kind of protective effect. A relative risk of greater than 1 implies that the exposure has some kind of adverse effect. We interpret this again in terms of times the risk. So a relative risk of 4 would be, the exposed group has 4 times the risk of having the event occurring than the unexposed group. 0.5 as a relative risk would tell us that the exposed group has 0.5 times the risk of having the event occurring compared to the unexposed group. So to recap, we can impose structure on random phenomenon by talking about probability. It's particularly relevant when we talk about contingency tables in the context of calculating relative risk. We can take a contingency table, convert it to proportions, which we then treat as probabilities, and when the table is a binary set of categorical variables, we have a binary exposure and a binary event, we can calculate relative risk, treating these proportions as probabilities and using the basic rules of multiplying and working with joint probabilities.